All right, we're recording now. Are there any questions about what we did last time? Uh, Good morning, Rochelle. Thanks for returning safely. All right. All right, we're gonna start the section 5.4. I'm gonna look at section 5.4. So we're gonna consider the two-dimensional homogeneous problem, homogeneous system, x prime equal pxy and y prime equal qxy with p00 equals 0, q00 equals 0. That means 0, is an equilibrium solution. Okay, so that means the origin is an equilibrium solution. All right. So for in particular, we want to consider the case when pxy equal ax plus by and qxy equals cx plus dy, where a, b, c, and d are constant. Okay, so this is what we are looking for. So in matrix system, so we're looking at x equal to xy, and so we're looking at x prime equal ax, where, and this is equal to ab, cd, x. Okay, so we're gonna look at this system, a, b, c, d. We saw that the solution, so we saw before, the solutions depends on the eigenvalues of A and corresponding eigenvectors. Okay, so we've already seen this. All right. So this is where we are now. I'll give you a few minutes to copy things down. All right. So let's flip the board. So again, you're looking at x prime equal ax, where a is this is, let me give a number to this equation, 5.42, where a is a, b, c, d. All right. So if I look at a minus lambda I, that will be a minus lambda b, c, d minus lambda. To characterize, we need to characterize the solution. So we're going to look at why don't you compute this equation at the quadratic characteristic polynomials? All right, so this is a minus lambda d minus lambda minus bc equals 0. So we have 80 minus lambda a minus lambda d plus lambda squared minus bc equals 0. This is lambda squared minus a plus d plus plus ad minus bc equals 0. So this is the same as lambda squared minus a trace of a plus determinant of a equals 0. Remember, the trace of a is a plus d. You add these diagonal. This is called the trace. All right? So if we let a p equal a trace of a equal a plus d, and q equal determinant of a, that is ad minus bc, then we have lambda squared minus p, this is a lambda, minus p lambda plus q equals 0. There's a lambda here, be careful. Minus trace of a times lambda. Okay? Any questions? All right. So lambda equal to p plus or minus p squared minus 4q over 2. So that is equal to p plus or minus the square root of delta over 2, where delta is trace of a squared minus 4 determinant of a. Okay? So, of course, any questions so far? So the signs of lambda depend on this is called the discriminant. Discriminant delta. What type it is. Okay. Okay, so now we're gonna discuss several cases of this. Okay. So let's say these are lambda 1, 2. Let's call them lambda 1, 2. So let's say lambda 1 is P plus, lambda 2 is P minus. All right? I will be flipping the board, so just make sure you finish. All right. I just want to tell my student from last semester that the book is in production now. The book we used last semester. And it should be out on the market by August. It's already, if you do a search, it's already on the market for sale, but for pre-order. But I believe, depend how quickly I respond to their emails sometimes because I'll be traveling. But I believe the book should be available no later than September. All right, that was a very quick one. And thank you for all your help. So I think you have the latest copy from me, electronic copy. You have the latest one. This is the one I sent to the publisher, and they accepted it as it was. Now they're gonna go through, read it for grammar and commas and punctuations. And if there's any changes, I agree to them, and then they will be printed. So basically, this is how the process go now. All right. Any questions? All right. So let's discuss this in several cases. I'm not going to go through all the details, but I will discuss. So the first case, real and distinct. That means this is the case when delta is positive. Okay? All right. So A if both lambda 1, lambda 2 are negative, then the origin 0, 0 is asymptotically stable. Okay? And that is 5.1a. So see figure 5.1a. So basically, this is the origin. This is the line. and all other curve will go like this, and they will go toward the origin. Okay. So these graphs only work for 2-dimensional. So don't expect anything else. That's why we do it for 2-dimensional. Plus, it's easy to quantify the eigenvalues. I mean the signs of the eigenvalues, of course. All right. B, if lambda 1, lambda 2 are positive, then 0, 0 is unstable. Okay. All right. All right. It's called unstable node. Some people use the word node. All right. C, if lambda 1, lambda 2 have opposite sign, then 0, 0 is unstable, and called a saddle point. Okay. So basically, for this case, you have one stable eigenvalues. Sorry. You have one stable eigenvalues. That is this one. And then everything else, one will be, they will be coming like this and going out like that. And things will be going like this. And things will be going like that. Will be going out. So the arrows only for the real line, this is the eigenvalue when lambda is negative. And for the other ones, you will have curves like that around them. So this is called a saddle point. Two real and equal roots. Okay. So basically, if you look at it, when you have real and equal roots, that means, so this means delta equals 0. All right. And again, here delta is a positive 2. And this delta positive, here delta is 0. All right. And if you see delta is 0, look what delta is. delta is p squared. So if p could be 0, so if you look at a q, so what is a and c equals 0, a and d are equals 0. Now b and c will be there. All right, so this is the case. So in this case, real and equal root. Now, of course, real and equal roots. So that means the delta is positive. And so the case is lambda is less than 0, then 0, 0 is asymptotically stable. Okay? Lambda positive, then 0, 0 is unstable. Okay? Of course. All right. Okay. I still have something to do. 140, 142. All right. And so basically, in this situation, solution are in either if lambda is positive, remember, if delta is 0, so lambda depend on p. So if a plus d are negative, then there you go. Then you will get stability. If a plus d are positive, you get unstable. All right. So we still have complex root. And this is delta is less than 0, right? All right. If the real part is negative, so basically you're going to get lambda equal to alpha plus minus I beta. Okay? Real part, if the real part is negative and beta is not 0, okay, then solution spiral to 0, 0. So here, asymptotically stable. So in a sense that, so you will have your solution like this. You see? They will go toward the origin. Now, if alpha is positive and beta not 0, solution spirals away from 0, 0. In this case, the solutions are you start near the origin and you start going away from it. So your arrows are like that. Okay? So you're going toward the origin, you're going away from the origin. So this is unstable. Okay? Now, if alpha is positive, the real part, and beta is not zero, it doesn't really matter what beta is in this instance. If alpha is not zero, the real part, then 0, 0 is unstable. Now, case B, a pure imaginary roots. So that means alpha is 0. So lambda is plus or minus I beta. Okay? In this case, solutions looks like x equal to C1 cosine beta t plus C2 sine beta t. Okay? This is what the solution looks like. And then if you square it where x is, x and y, you can easily find what the corresponding other solution is. And if you take the constant to be 1, so basically you got the solution x squared plus y squared equals some constant c squared. So solution stay along the curve x squared plus y squared equals c squared. You know, this is circular. So in this instance, solution are like this. And here, 0, 0 is stable. Okay? So the origin will be stable. All right. Any questions? That's all what I wanted to do on this section, really. Not much there. Okay? And I'm going to move on to another things. So take a look at it, see if you have any questions. Any questions? I mean, you can do so many examples, but I mean, I have the pictures in the book. You can take a look at them. All right. All right. This is 145. 146. Now we're gonna take a look at a different idea, depending on how far I can go. Okay, this topic is important for student in engineering. So, we're gonna look at section 5.5. I don't know if I'm gonna look at the gradient system, but I'm gonna look at the Hamiltonian system for now. Hamiltonian systems. All right. I am looking for some example 3.5, so bear with me for a second. So I can find it. So we have the pendulum from example, let's see. I don't have a number attached to it. From the example, on page 69, we have the pendulum. ML theta second plus mg sine theta plus BL theta prime equals 0. You can look at the picture over there. And so by letting x1 equal theta of t, x2 equal theta prime of t, we rewrite this example. So we're going to have x1 prime equal theta prime equal x2, and x2 prime equal theta second. That is minus mg over ml sine theta minus bl over ml theta prime, or x2 prime equal minus b over m. Let me write it in, it's minus g over l sine theta, but theta is x1, minus b over m, theta prime is x2. So we have the equation of the pendulum, x1 prime equal x2, and x2 prime equal minus a g over l sine x1 minus b over m x2. Okay? So this is equal in system form. This is the equation of the pendulum. Any questions so far? All right. So what I'm going to do is I am going to define the energy function H from T0 to alpha cross R2 into 0 to infinity by H of x1, x2, that is 1/2 x2 square of t plus g over L 1 minus cosine x1 of t. Okay? All right? Can anybody tell me in terms of physics what these functions are? Do you have an idea?
Looks like kinetic and potential energy to me.
Very good. This is the kinetic energy, and this is the potential energy. Okay? Is that clear? So let's evaluate this function along the solution and see what happened. You see, this function is positive. So h of x1, x2 is positive. All right? And h of 0, 0, if you notice, is equal to 0. Why is it a positive? Because cosine x1 is always either -1 or 1. So in either case, if it is 1, you will get 0, you'll get x2 squared here. So, and if both are 0, you have 0 here, cosine 0 is 1, 1 minus 1 is 0, so h of 0 is 0, and h of x1, x2 is always positive. Okay? Except at 0, 0. And notice this system, 0, 0, is in equilibrium solution. Is an equilibrium solution for the system. All right? Why is that? If you set x1 prime equal to 0, you get x2 equal to 0. You set x2 prime equal to 0, but x2 is 0. That means sine x1 is 0. That means x1 is 0 between 0 and the pi. Let's put it this way. Okay? I mean, you get more equilibrium point. Let me put it this way. Actually, the equilibrium point are plus or minus n pi 0, because x2 is always 0 and the sign is 0 at a multiple of pi. Multiple mean by integers. So like a pi minus pi, 2 pi minus 3 pi, so forth. So your equilibrium solution are plus or minus n pi, n equal 1, 2, 3, and so forth, and 0, 0 for n equals 0. So we're elaborating here on the 0.00. Oh, for now. Okay. Now, so this is H. So let's compute d over dt of h of x1 of t, x2 of t. Well, that is del h over del x1 times dx1 over dt plus del h over del x2 times dx2 over dt, right? Chain rule. Okay. Any questions? Well, what is that? Del h over del x1 is del h over del x1. You got this one. Sine x1 times dx1 over dt times x1 prime plus x2 del h over del x2. You'll get 2 partial credit times x2 prime. So this is sine of x1 times x1 prime, that is x2, plus x2 times x1 prime, x2 prime, minus g over L sine x1 minus b over m x2. Okay? Okay, let's see what I got here. I forgot here that I have here, if you take the partial with respect to x1, you get g over L sine x1. Okay? All right. So as you see, this term go away with this term, and we are left with minus b over m x2 squared. Correct? So what's going on here? If the friction of the pendulum, if the friction B is positive, then dH over dt is negative, because that's dH over dt is negative, and the energy is dissipated. Is dissipated. Okay? On the other hand, now if B is 0, the friction, there's no friction, then dH over dt is equal 0, and the energy is conserved. Okay? So what does that mean? Thus, if B equals 0, dH over dt equals 0, which means if you integrate h of x1, x2 equal to constant C. Okay? So which is level curves that the solution will stay on. Will never leave them. In other way, these are the solution. And any solution with initial condition that will go eventually will go to this level curve and stay there. Okay? So now this is not the case if B is positive, of course. All right. So when energy is conserved here, B equals 0, okay, we obtain an example of Hamiltonian system. For us, that means setting B equal to 0. What do we have? We have x1 prime equal to x2. x2 prime is minus g over L sine x1. So that is Hamiltonian. This is a Hamiltonian system. We're going to look at it in details and see what happened. So what does this mean? So if we look you see H is independent of the friction B. So remember, this is our H. X1, X2 equal to that. Notice, what is X1 prime for us? X1 prime equal to, by definition, from here, X2, but that is, if I take the partial derivative of H with respect to X2, what do I get? That is del H over del X2 from here. Do the partial derivative and you will see you will get it. And X2 prime is, what is X2 prime by definition? Now B is 0, remember. Oh, here, we're looking here. X2 prime is minus G over L sine X1, but that is minus del H over del X1 from here. Take del H over del X1, this is 0. You'll get a G over L times the derivative of minus cosine. The derivative of minus cosine is sine. So you'll get G over L sine X1, but here we have minus, so it's minus del H over del X1. So basically, in other words, for a system, x prime equal pxy, y prime equal qxy, there is a function h in terms of xy, so that x1 prime equal to I said x2 and I'm talking about x prime. X1 prime is going to be, the q is going to be del H over del X2, and X2 prime equal to minus del H over del X1. But by definition, X1 prime equal to P of XY, and this one is by definition equal to QXY. You see, in other words, for a system x prime equal to pxy. Okay, well, in the book I use f and g. I will get back to it. And so this is what it should happen. If you have a system x prime equal to pxy, y prime equal to qxy, this system is Hamiltonian in the sense that energy is conserved. That's what it means to be Hamiltonian. The energy is conserved along the solution. Then this is what you need to have. Just a second. Okay? Any questions? All right. So this is a good example. The pendulum is a good example about how energy is dissipated or conserved. And in the case it's conserved, it is a Hamiltonian system, and we kind like step by step got to where does it mean. So I'm going to make this as more formal in my next definition. All right. Any questions so far? All right. Sorry. Any questions so far? Now I'm gonna be in so in our example, the level curves are h of x1, x2 equal constant, or 1/2 x2 squared of t minus a g over L cosine x1 of t is equal to c. Okay? These are the level curve. Because we said it's h, because we showed that the derivative of h with respect to t is along the solution is 0. You integrate that, you get h x1, x2 equal to a constant. All right. So this is a definition now, 5.5.1. Okay. A planar system. So that means planar system means x prime equal f of xy, y prime equal g of xy. This is what it means. Planar system. Of differential equation is called a Hamiltonian system if there exists a differentiable function okay, so I am using x1 prime, x2 prime instead of x1 y. Okay, I'm using this. A planar system x1 prime equal a function of x1, x2, and x2 prime is a function of g x1, x2. Of differential equation is called a Hamiltonian system if there exists a differentiable function hx1, x2 such that, okay, just a second, guys. Record. Dash. Lhasa. Variação. ما تعذر ما تعذر بيردوا بس ما حاولي بس شيء اوتوماس في يدك يا اخي ما في اخذ لا لا تودي لا لا تودي يعني انا عارف ده ما كيف يعني والله ربط خبر كيف الا ما تظبط الابلكيشن على التليفون ما طيب بخليها معك شو كيفهم لا ما اعرف شو كيف هذا زي اسحب ايه بس قلت لي بدك تحط صوره ما ضل تحط هيك ما بعرف اذا طلعت الجيران خليك معك All right. Sorry, guys. You have to listen to this. All right. If there is a Hamiltonian function is such that x1 prime equal del h over del x2 and x2 prime equal minus del h over del x1. And we're going to call this is 5.5.2. Such a function is called a Hamiltonian function for system 5.5.2. Okay. Now we're repeating the word Hamiltonian. Actually, this is the name of Hamilton. I think I'm not sure if he was a French mathematician, but he was an European mathematician who worked on, he was a physicist and mathematicians. And I have told some of my students in my past classes that in the 1700s, when all this math was flourishing, there was nothing called Department of Mathematics. Thus, scientists got together and they worked on what they had to work on. And when they encountered a math problem, they worked on it. And they got what they wanted at that time out of it. And then later on, when mathematics was getting refined later on in the West, in the US, and math departments started to exist. And then mathematicians start working on all these theories and improving it because there was a lot of gaps in the middle of this theory. I mean, engineers look at things differently. But these people, the engineer people, physics people, math people, were the original to initiate all this work. And then later on, it was all refined. Okay? So I can, what I'm trying to tell you, I don't know what Hamiltonian was. Was he a mathematician? Was he a physicist? Was he an engineer? I really don't know. As I said, they encountered the problem. If it was in Europe, mostly like related to ship sailings, trying to go to different countries for wealth for the countries. So they needed navigation tools and other things. So they worked on mathematical models. All right.
I thought Hamilton was a founding father.
Huh?
Bad joke, sorry. I said I thought Hamilton was a founding father.
Of
Sorry, bad joke.
yeah, we did have a president as the name Hamilton, didn't we? Didn't we? We did, didn't we? Hey Nancy, didn't we have a president of the US named Hamilton?
Hamilton was never president.
Okay, my wife is saying he was never president, right?
No, I just said he was a founding father. He was never president.
So did he write like the Constitution or something?
He was instrumental in an early form of the Constitution, and in the Constitution, and then he also was the founding father, mostly involved with starting America's Bank.
Oh, okay. Well, he did a good job then. All right. So no, that guy was a scientist, the one I'm talking about. Yeah, my wife is saying he's on the $20 bill or something.
Yep.
Yeah. All right. So now I do have a picture for the pendulum, how centers occur on page 148. You see the level curve. These are the level curve, and you have centers around the origin, around 2 pi, around minus 2 pi, because those points uh, um, are all equilibrium solution. All right. So So let's take a look at I'm on page 148. X second minus f of x prime minus a g of x equals 0. And you know the prime mean d over dt. Okay? This is a prime mean d over dt. That means x is a function of time. Then this can be written as x1 prime equal x2 and x2 prime equal to gx1 plus ffx1 x2. Okay? So what is a Hamiltonian function for that? Okay, so I can define let h x1 x2 equal 1/2 x2 squared of t plus or minus 0 to x1 g of s ds. Okay? So let's take this one and so this is a kinetic energy. This is the kinetic and this is the potential. Okay? And if I look at del H, I am looking here at del H over del X2 is 1/2 times 2x2 times x, no, that's it. And that is x2. And look at it there. Okay? And then minus del H over del x1 is minus of minus gx1 times x prime. Because you need, this is x time of t, and I'm differentiating. And then this is okay, that's I'm doing with respect to I'm doing with respect to x1 only minus gx1. So there is no prime because I'm not doing the derivative with respect to t. And that is let's see, x1, x2 prime. Okay, let's see. X2 prime is g of x1 so this is g of x1. Okay, so this function, this Hamiltonian function is Hamiltonian only if the function f of x1 equals 0. If f of x1 equals 0. So what does this mean? This implies that x second plus g of x equals 0. This implies that the Newtonian system, the Newtonian system, x second plus g of x or minus g of x equals 0 is a Hamiltonian system. Okay, so this is a Hamiltonian system. Well, I mean, what did we do? So basically, you got x1 prime equal x2, x2 prime equal g, x2 prime equal g of x equal to g of x1. Okay? And you take this Hamiltonian function, and then that should work. Okay, let's see. I hope I don't have a typo. No, I should be all right. All right. Any questions? Because I need the minus. All right. I need the minus. Okay. Any questions? So any Newtonian system of this form, x second minus the g of x, like, can you give me an example what this is? It's like the spring problem, right? Any mechanical problem. I mean, you've noticed x second plus omega squared x equals 0. So this will be g of x. So that is a spring problem without friction. Okay. All right. Any questions? Okay. All right. Now we're going to try to all right. So again, recall x1 prime equal to del h over del x2, x2 prime equal minus del h over del x1. This is 5.5.2. And I'm saying if you such system, okay, such a system conserve the energy. To see this, we look at dh d over dt of h of x1 of t as we did before. That is del h over del x1 times x1 prime plus del h over del x2 times x2 prime, del h over del x1, that is minus x2 prime, x1 prime, plus del h over del x2 plus x1 prime x2. Okay. And what is x1 prime? Just, okay, okay. So no, I really didn't want to do that. So let's save ourselves one line. This is del H over del x1. X1 prime is del H over del x2 plus del H over del x2 times x2 prime minus del H over del x1, and that is a fat zero. So the energy is always conserved. So if you can find such a function H so that your system, your original system is in such a way, then your system is Hamiltonian. All right. A Hamiltonian system, Hxy, is always defined by Kxy plus Vxy. This is kinetic energy, and this is the potential energy. Okay? Kinetic energy and potential energy. All right. Any questions? Now let's find a criteria without, you see this, I mean, I'm sure some of you are sitting back there and wondering, is Dr. Raful talking about conservative vector field? Do you remember from Calc 3? This is a very similar concept to it, except we don't present it like this to our student. Okay? We don't dare to tell them this is the energy function and this is and that, this is kinetic, whatever the vector field is, so forth. All right. Any questions? All right. I'm gonna now, this is taking longer than I thought it is, this lecture. I thought it would go fast, but I'm really taking my time. So I want you to understand this concept as engineers. So again, let's consider x prime equal f of xy and y prime equal g of xy. I mean, you can use x1, x2. I'm going to use xy. 5.54. So I think my next job is, for now, since my latest book is in the publisher, and I'm going to get bored very soon, I think I'm going to inquire about writing a second edition for this textbook. I think I can improve it a little bit after I taught out of it for like 3 times now. So usually the wait is about 5 to 6 years, provided the book is profitable to them. All right. So again, based on this 552, system 5.54 is Hamiltonian if del H over del Y equal f of xy and minus del H over del X equal to g of xy. Well, let's take a look at it. Why? Because x1 prime is del H over del x2. That is this one. F of xy is del H over del y. And for the other condition, we need del H over del x1 equal to x2 prime, but x2 prime is y prime is this one. So this is one of the requirements. So let's see when 5.5.4 is Hamiltonian. Without referring to H. Well, so let's work with this. What is del over del X over del H over del Y? That is del F over del X. Okay. Okay, let me start instead. Let me start with this. Del F over del X equal to del over del X of del H over del Y. Now I am assuming that the function H has a continuous mixed derivative, mixed partial derivatives. Actually, I require that to be a continuous, has a continuous first partial derivatives, regardless whether they're mixed or not. And this is the same as del over del Y over del H over del X. And that is del over del Y. What is del H over del X? Is minus GXY. Okay? So we showed that 5.5.4 is Hamiltonian if del F over del X equal to minus del over del Y of a G, without knowing what H is. If you can show that, which is very, very easy, Calc 1 student can show it, that this is really not bad. It's easy to show. Any questions? All right, so let's take a look at an example. Excuse me. So let's take a look at x prime equal x plus y squared, y prime equal minus y minus x squared. So this is F, this is a G. So I need del F over del X. That is 1. Del G over del Y. That is minus 1. So we see del F over del X equal to minus del G over del Y. So the system is Hamiltonian. Is Hamiltonian. Okay? Now you may write this system, we can write this system xy prime as A as 0, 1, 0, and 0 minus 1, xy plus y squared minus x squared. I can write it like this. We will study this later. Some student who had me last semester, we talked about this system. So if I look at this, what's going on here? And so this is x plus y squared and minus y minus x squared. If you look at the eigenvalues of this function, so you get lambda equal 1 and minus 1. Okay? So you will see that the origin is not stable. And we're going to get to that later on to show some stability result next time. So I will finish this next time, and I will leave you with this. I'm going to ask you to read theorem 5.51. And so next time we'll go a little bit faster. Okay? Any questions? I am intentionally slowing down a little bit. So, I mean, it's always been my idea, as you understand, a lot of what I do in class. I don't want to send you home where you have to do all the work on your own. And on your own, you can fill in the gap by looking at the book and so forth. All right, any questions? I have three questions here. No question here. Kinetic and potential energy. Very good. Andrew Jackson is on the $20 bill. Oh, yeah. Not okay. Hamilton Jackson is on the $20 bill, not Hamilton, honey. Hamilton is on the 10. You see, my student will correct you. They don't. I taught them not to be shy. How's that? All right. Any question, guys? Now, it happened on Juneteenth. When is Juneteenth? On the 19th? What is Juneteenth, Nancy?
It's next week, Friday. It's the 19th.
Yeah, but unfortunately, we don't have a class. So what happened is we'll take a day off the last week of classes, okay? We'll see. Because I think we're going in good pace. Okay, I said Jackson is on the 20 because he abolished the original bank of the US, if I remember correctly. He abolished the original bank of the US. I don't know what that means. All right, guys. Anyway, nice seeing you again. I will see you tomorrow.
See you.